So we briefly talking about system call implementation and hardware interrupts in the protection lecture, and some concept of protection and scheduler and process concept of process. Okay. And then the main thing is synchronization parts, not yet, and memory management. Memory management is today focus. And file system and I/O system later. Okay, so this part we will learn later in the after midterm period. Okay, so that is the key memory management is key focus of today. So when I start talking about memory management system, I introduced this concept of level of indirection. So an example of a level indirection was pointer, where pointer itself doesn't have a value. So pointer pointing its address. This address is reinterpreted. So to reference interpreted and finally get the value. So when I kind of illustrate the level of indirection, I say this is kind of one domain, and there's the other domain, word space that is indirected by some function. That is concept of level of indirection. So what kind of this level of indirection having a benefit when this area may be contiguous but not necessarily in the corresponding part. This part may not be contiguous. This function create mapping of this contiguous space to non-contiguous space. This is one example of level of indirection. And also we can make a sharing. So if there's two different domains having the same pointing to same domain, so it can achieve sharing. Level of indirection providing this flexibility of this space, this domain and this domain. So someone say that most computer science problem is solved by this adding new level of indirection. Okay, so we learn the concept, right? So this is also kind of continue recapping of what you learned previously. Virtual address, design of virtual address space are closely related to protection. Okay, so protection is the case where when operating system loading multiple processes in memory. So typical way of learning or providing protection is in the physical memory. Without protection in the physical memory, if application or operating system learning multiple processes in the same physical memory, they are not protected each other. Okay. Therefore, this causes serious protection issue we talked about. Okay. For example, this on illegal memory access from other processes, which makes a process can read, modify code and data of other processes, also operating system. Okay, so this should be protected. So to allow protection, concept of we learn the basic way of learning protection is making each process one process to run in separate address space, AES1, AES2, different address space. Okay, so what kind of mechanism allow this different address space using virtual memory? So virtual memory is contiguous address space or created by hardware, and this address space are translated into physical memory. So that is key core concept of protection to protection. So therefore, process 1 and 2 are running in different address space, cannot read and modify other process data because they are not in same address space, meaning that a process cannot kind of pointing data in different address space. So we learned that. Okay, this is recap. Okay, so again, to address space, there are two. For protection, there are two address space. Okay, virtual address and physical memory. So there's a hardware called memory management unit, which it checks is legal and illegal. Hardware check it. If it's not legal, what happened? Then it caused some exception, which is called page fault. When exception happens, we learned that how kernel, what is exception and how exception is handled in the earlier lecture. So control goes to kernel. The kernel decide whether it can kill the process or continue to execute the process. The kernel can decide it. So page fault giving a chance to kernel control this illegal memory access. Okay? So this is also kind of basic way of implementing virtual memory, right? So question: this design about this virtual memory, we can think about virtual memory is a kind of level of indirection. So mapping this virtual memory design to original concept of this level of indirection, what are levels? Clearly, what are levels? What are the levels? Level virtual memory. And the other one is physical memory. Address is more better way to put it. Address, physical address. Okay. Who perform indirection? MMU. Okay. Memory management unit allows this translation. Okay. So that is concept. So that's actually kind of most important aspect of virtual memory design. What kind of benefit you can get from this level of indirection, we will discuss. But the thing is that for protection and for flexible management of this virtual address domain and physical address domain, level of indirection provide way to many benefit for this operations. For example, using this one, protection is, for example, that I gave you, and later we're talking about management. So separating management of virtual address space, one level, and separate and this management are completely separated because of there's indirect function between them. So it makes management easier. So virtual memory management, physical memory management is separated. And also I say that contiguity. So when virtual address contiguous, physical address not necessarily be contiguous. That allows to also giving some kind of easier management. So protection and management is most typical example. We can get benefit from the using level of indirection. So let's talk about that. Protection, we already talk about that. Management throughout this course, I will keep talking about that. All right, that leads to some design goals of virtual memory. The first goal is obviously protection. So I keep talking about that, so I don't talk about that. I don't recap this requirement of protection. The second one is transparency. Transparency is also important concept for application. So process. So let's talk about what is the concept of transparency. Process should not aware of that memory is shared, for example. Okay, so build process. Process using this some of the virtual address space, creating virtual address space, deleting virtual address space, and underneath, under the hood, operating system can map this virtual address space to physical address space, and how this mapping happen are completely hidden. So process cannot aware of what happens in virtual to physical memory mapping. What process can see is contiguous space of virtual address. That's it. And it doesn't care about what happens here. This is kind of OS managed. So even for example, process cannot recognize whether page fault happens or not. Process cannot recognize whether memory is shared or not. All operation is hidden by hidden by operating system. Therefore, process just kind of using the contiguous virtual space, which is called transparency. Operation is not shown. Operation is transparent to application. It's called transparency. And obviously, the other one is efficiency. So efficiency in terms of performance, in terms of space. So space should be saved, and there's some kind of hardware support for performance. Efficiency and transparency. Transparency and protection is 3 requirements of virtual memory. So let's talk about that. All right. So address space. Some part of this lecture are overlapped with protection lecture. So that part I can give you some brief explanation, but some part does not. So let's look at virtual address space. If you can zoom in the virtual address space, which is it is just an illusion of private, meaning that per process space. So virtual address space typically consists of this read-only segment, which is kind of init text read-only data. So usually someone say this is code section, okay, and read and writable segment, which is called data and BSS. Data and BSS also someone simply say this is data. Okay, so again, this section is also known as static area. And the other section, heap and stack, is known as binary area. So static area is allocated on exec. And code and data. So it means that this section is created and allocated, filled on exec system call. If you look at the PinToS in the PinToS exec system call, this section is initialized. Okay, I recap this question. Just for recap, do you recall that where read-only this data and this read-write data comes from? Where do they come from? Where do they come from? Okay. So in your storage, there's a binary data in ls. Here, the code and data section are coming from this binary. So this process, reading this binary data into memory, we name this kind of an operation. We name this kind of special operation. What is the name of that? What is the name of it? The process where reading code and data to memory, loading. Okay. This is called loading. Okay. However, this dynamic data is not in this binary. So it allocated at what? Runtime. Okay. And it can grow and shrink. This section size is fixed in the binary, but this section is dynamically changing. So we can say it's dynamic data. So heap and stack is example. So probably we will discuss later, but how this section is allocated. So they are filled from binary data, but you say you allocate heap. How this section is allocated? malloc. Okay, we'll discuss the malloc operation. Malloc is actually not a system call, but we will specify later. So malloc, and then when we call malloc, what happens underneath, we talk about later. But for now, this section, the data contents are stored in the binary. But this section, there's no storing contents. So what is the contents of that? What is the contents of it? What is the contents? Register? No. Register, let's say this content initially allocated, then you start to use it. So this section, when application first starting to use it, loading data from the binary. But here, this heap section, how this data gets filled? Where does it come from? Anyone can guess? Operating system locate local variable. Local variable is just kind of variable, but before using the local variable, cache no. Simply. So when this section is allocated, operating system make a paste and zero it and give it to process. So this section is allocated runtime, but field 0 and give it to process. Okay, so it's not from the user code. It just created from the operating system and make it 0 and give it to process. This is the kind of characteristic of dynamic area. We'll visit later. Okay, so therefore, these 4 sections are important, and also, as I say, this is a kernel section where row end part used by a process, the high end part used by kernel. So when application make a system call, when kernel created, kernel create virtual address space. So every process has shared this kernel part, which also contain kernel code, kernel data, kernel heap, kernel stack. So system call meaning they're jumping to kernel. So user level code jumping from user level code to kernel code. So direct jump is not allowed. Therefore, we need a special instruction like system call. Recall that system call is also Sys call is also some instruction that cause trap. So if you make a system call, like a page fault, exception happens, then control transport from user level code kernel. How to return from the system call? What was the instruction that returned from the system call? Do you remember that? In the virtual address space? Or you also some is possible to also use IREN, come from internet, but sysred is the most common instruction they use. Okay, that's it. Right, so then the control go back to user level code in the virtual address space. So when this is kind of later virtual address space. Again, I want to emphasize again that this is for each process. Right, so that is a virtual address space, and we kind of elaborate the concept of virtual address space. Sorry, it seems like hold on. I think this slide is not updated. Oh, I'm sorry. But I'll let you know. I will talk about it later. Okay, so before this is kind of summary of virtual memory, but before that, I want to kind of explain this one. So because this process virtual address space, this one, so it's process one one process having a thread has this stack and code and heap, and the other process also having this code data stack and heap, and this address space, virtual address space 1, virtual address space 2 are mapped into physical memory. Okay, so this is concept of level of indirection, virtual address here, and there is a specific address translation mechanism. The next lecture, we will deeply looking at what kind of mechanism are invented for this translation. Branch and bound, segmentation, paging, multi-level paging, etc. We will discuss each different translation mechanism. Okay, so this is of two level, and there are several indirection mechanisms. So therefore, different indirection mechanisms will be discussed later. Okay. Second thing. Sorry, I think I created this one in the slide. I will update the slide later. So sorry for that. But this is one important thing I want to explain. So at some point, this virtual address space and this physical space having create a mapping. Mapping indicate that when application can start using physical memory. So that leads to this question: when allocate physical memory. When. So key word is when. So application having a virtual address space. And physical address space, the mapping has to be created. When. Creation of process, good point. So let's kind of bring up the idea. When application created, mapping created, fine. Then let's say a process uses 1 terabyte. Then do we want to allocate 1 terabyte memory? Okay. So exactly. So it goes to more when a process actually use it. So use it. What does it mean? Use it. So this virtual address space, for management purpose, different mapping mechanism has different granularity, but let's take about some paging mechanism where it actually creating address space some kind of chunk, say 4 kilobyte chunk. Physical memory 4 kilobyte chunk. Use it means that application trying to use the virtual address space, then who create this mapping? Who create mapping? Who create mapping? MMU use it. MMU use the mapping, but who actually make this mapping between virtual to physical? Or for OS. This implies that when application use it, operating system has to take a control. Okay, operating system know that when as soon as process try to use a virtual address space, operating system has to know how. How does operating system know? Exactly. So page default to exception. So initially there's no mapping. Then what hardware does is that if no mapping exists, then raise page fault. Okay, so no mapping, raise page fault. So if page fault happens, sorry, I make this content in the slide and I put it, but I think it's not updated in it's not updated in my Google Drive, so I just kind of draw it, but same content I will deliver it to you. So when page fault happens, a process completely stops because of page 40 exception. Stop. Then this is a user. This is kernel. Then kernel takes control. Who? Page fault handler. Who raise a page fault? Process or kernel? Process. So process are running in the process user space. When process start using the virtual address space having a no mapping, then CPU raising a page fault in the process context. Then the page fault happens here, right? In user level context. Then control transfer to kernel. And it's specifically the the page fault handler. Page fault handler get free page. Okay, sorry. Allocate page. Then there is a in the same physical memory manager. Ask it. Then get free page from free list. Typically, Pinterest and Linux implement this page as a free linked list, so get free list. Then 0 the page. Then give it to page fault handler. Page fault handler create mapping. Then a process resume. At this point, process access this virtual address again. Then page fault happens or not? Page fault happens or not? No. Then process can continue. So that is called demand page. When application use page fault happen, then when page fault happens, goes to kernel. Kernel allocate a page and create a mapping, and then resume. Then next time process access it, no page fault happens, then page kernel is allocated. Okay, so that is kind of key one design question to design for physical memory allocation called demand paging. Question: 0 the page. Why kernel has to 0 page? What if skip? Is it okay? If you think this skip is okay, click yes. If you think skip is never, it always required, no. Could you click yes or no? If skipping is possible, yes. If skipping is never, we should always 0 pages, click no. Click yes or no button in the reaction. Could you click yes or no button? Go on, please. All right. So around 80 students say doing this kind of poll. So answer is never. It should. So answer is no. We cannot skip at all. What happened if skip the pages? Skip the zeroing page. What happened? What happened? It can then what's the problem? A process. Okay, is it okay to remove this content? It's okay if everyone write down. Okay. So I will kind of eliminate it, right? So, okay. 0 page. If not, then let's say a process. Process 1, 2. Process 1, on map. On map is operation where free memory on map page. So it has some contents. Try to map, then it operating system give it to process. Therefore, without zeroing, a process can see the contents of process 2, which violates design requirement. What's the violation of if this is allowed? What does this implement design violate? These requirements? Protection requirements violated. Therefore, no. Always have operating system 0 and give it to process. That's required. Similar question. Thread, mellow, and free. So some pages are free, and the other thread try to mellow. Then memory allocator. Does it 0 and give it to other thread or not? When you allocate memory, when you free and mellow again, is it always 0? No. Why? Why is possible? Why this design? Why this is performance, right? If you can skip 0, we are fine. But why memory allocator does not 0? Okay. No protection between thread. Okay. Therefore, it's okay. This design does not violate fundamental protection requirements. It's okay. All right. Someone asked a question. What if process is fork? What if the process is fork? Do we still need to empty? No. Recall that in the process, we do copy on line. Operating system performed copy on line where parent and child having the same mapping. Remember that? So they were 0 there. So 0 only happens when allocating this dynamic part of the area which is stack, heap, and stack. Okay, heap and stack, when allocating heap and stack, operating system 0. Code and data, operating system reading data from binary. They're two different. Okay, so that was the one important, the thing for virtual memory. So that leads to this basic design concept. This is a recap of virtual memory design. Each process on virtual address space, obviously, and this is large and contiguous. And virtual address space are private to each process. I keep talking about that. Second, this address translation is performed at runtime. So I discussed that in different address translation mechanism later lecture from virtual to corresponding physical address space. Second, it supports lazy allocation. Physical memory is dynamically allocated and released on demand. I just talked about that. Demand paging. So our program execute without requiring entire address space to be resident in physical memory. So if process want to use 1 terabyte, 1 terabyte is not immediately allocated. Once process start using it, operating system allocate gradually on demand. Okay, that is key 3 requirement for design outline for virtual memory. After talking about basic abstraction and design requirement, then what's the next thing we have to talk about? Recall, the other process and thread lecture. What's the next thing? What is the next thing? Exactly. Then we can talk about how to use this abstraction in API. Okay, API. So memory API has three layers: application's perspective and operating system's perspective. There is some kind of a layer in the middle. So where? So application using malloc and free. Okay, then libc in turn brk, svk, mmap system call. Application directly using the brk, sbrk, and mmap system call we'll talk about later, but most common application using this interface. So do you remember that you implemented the memory allocator in systems program? So in application libc operating system, where is the memory allocator? You just which part implementing memory allocator? Malloc memory allocator. Where is it? But including, okay, libc. Memory allocator are here, which actually turn malloc API, application API, brk. So does operating system have system call name malloc free? No. For malloc, we're using this brk sbrk map. For free, munmap. System call are translated. So to manage application, malloc, free, calloc, realoc, and libc are memory management. The memory manager implementing this allocate virtual address space. In turn, these things are translated to and actually kind of allocating memory that is translating to this SPK, SPPK system. This one only relates to where? What part? Heap. So malloc, does it allocate stack memory? Does it allocate stack memory? No. So how stack part is allocated? There's no API for increasing stack. How does stack is allocated? So these are explicit API for allocating memory in the heap area. So is there API to using allocate thing in the stack? How do you think? Okay, so stack, no, stack is that, like this one. So if this is, let's say 4 kilobyte, and if you are put local variable, then stack increase. So here is the stack pointer. If application trying to using more memory than stack pointer access, then what happened? What happened? Page fault happened. Page fault happened. Okay. Stack overflow is that stack is the written, but I'm talking about the legal allocation of stack memory. So page fault happens. So by increasing stack pointer, so operating system allocate 4 kilobyte memory again and increasing stack pointer according to there. Okay, so therefore stack is also allocated on demand as stack is grows within the 4 kilobyte. If it's allocate memory or trying to access stack which is not allocated in the page table, then page fault happens. Then operating system will transparently allocate stack. Therefore, there's no explicit API for allocating stack. Does it make sense? Okay, so we are focusing on heap. Okay, so malloc free API, you are already familiar with this API. So this is return virtual address space. This is size of malloc. Okay, so when application having this one, size of memory blocks in bytes and size of T is unaligned, unassigned integer. Return is a success. If in case of success, a void pointer, type pointer to a memory block allocated by malloc. And fail, it returns null pointer. Simple. And free is API, whether it takes parameter of freed pages, free allocation. The freed memory region is allocated by call malloc. So here's a kind of one, you also allocate memory by mmap. So there are both ways. Mmap is also a way to allocate virtual address space. If you put the mmap into mmap returns address, right? If you put this address to free, what happened? What happened? Is it okay? Yeah, it's not defined. So what happened? You don't know. It's just a good point, undefined behavior. So therefore, the virtual address allocated by malloc should be freed using this same API, because this mmap bypass memory allocator. So memory allocator does not know how to deal with this case. Okay, so it should be kind of a match. Okay, and return none. Spoil return. All right, so this malloc and free. So here's kind of a simple illustration of what happens in the malloc and free. So in function int pi, again, where the this location of pi, pointer pi, where is it? Stack and heap. Stack or heap? Simple question, right? Where is it? It's in the stack, okay? In the stack. And in the stack, you assign this malloc of this size. Then what happened? This pi in the local address space in stack, pointing to this 4 unit of integer, 1, 2, 3, 4 unit of integer, and allocated by memory allocator, and pointing the first address space, pi pointing to 2k in this case. And then this pi is freed. So this one first has to invalidate it, meaning that there's some kind of invalidation marquee there, and then this address space gets free. So that is simple operation of malloc and free. So this one has to translate into system call. But before that, I want to talk about two APIs. CLlog. So CLlog is a memory allocator API which augments some behavior of malloc. So for example, CLlog 0 before running. So if you are compared to malloc, CLlog takes more time because it's zeroing. But if I want to always having a 0 initialized by 0, then you can use CLlog. Reallog is also an interesting function where it takes the address PTR and size. So size is increased. Okay, so size is new size to increasing memory block. For example, I want to make a virtual address space. So this is my virtual address space. This is my kind of a size of 4 kilobyte virtual address space. I want to increase by 4 kilobyte more, 8. Then you can have some pointer of PTR, and get the size of 4 kilobyte. Then this PTR having a 4 kilobyte range of virtual address space are allocated. Reallog. If reallog fails, obviously return what? Null. Okay. Another question. So this PTR returns new virtual address space. So say reallog PTR size say 4 kilobyte, and it return address PTR. Do they same? Do they same or not? Depends. When address and PTR is different, when I'm just recapping what you learned in the systems program, right? If there is no space to increase, then what operating system does is finding some space where having a 4 kilobyte and moving the PTR and return to address space. Therefore, if there's some address space already taken, after this PTR value, then allocate new space of 8 kilobyte and making PTR to here. Therefore, original PTR and return address may not be different. May be different. Okay, so that's the semantic of real-log and CL-log APIs. All right, so that is the libc part of memory management API semantic. Memory management API for what memory APIs that memory management systems provide, and this memory manager, malloc memory allocator, use this system called BRK. So BRK is the system call that increasing heap size. If there is no lacks of heap space, operating system asks OS to expand heap. Question. So when application trying to using heap, okay, then what operating system do, what the memory allocate has to do is increasing BRK to point here. Let's say so some size, for example, 16 kilobyte are increased. Okay, BRK. Then, if application start using this heap, what happened? Access. What happened? Page fault happened. Then OS allocate. If memory manager forget to expanding BRK, so BRK keep staying here, but application may access this portion. Access. In this case, access. Increasing here without increasing. Access. Then what happened? Same PF. Then what happened? Then what is kind of correct semantic? You can guess. Kill. Okay. So process can use it illegal way. So operating system kill it. BRK is kind of specified it is. So a process can access unauthorized, unallocated memory, so kill. Allocated page fault happens, then OS can allocate pages. This is illegal access, then operating system kill the process. Take a port. More specific, okay? All right, so that is the break is the end of the heap in the BRK pointer. So therefore, malloc using the BRK system call to increase size of heap. SBRK is similar to BRK where it only has some kind of increment. How much size we increase? SBRK is more common APIs, and just for sure, never it's good practice to never directly call either BRK, SBRK. Otherwise, the memory manager does not know whether it has some state of BRK that application can using its own BRK system call that confuse memory allocator. So it's good practice to never directly call SBRK or BRK because it confuse the memory manager. Okay, so that's a good practice. BRK. Maybe it has one question. SBRK0. When you are doing some row-level programming, you may see this function SBRK0. What does it mean? Increased length is 0. Then what does it mean? get pointer what? Okay, exactly. Get current BRK. To get the location, SBRK0 returns current BRK location. Sometimes you use it. Okay, so that is some BRK system call, and then one of the most general and important API, mmap. Mmap is the most important API in the system. So with the emphasis of memory and the all other systems, file system and device, mmap is most important. So let's talk about that. Mmap is kind of separate two parts. First, in this lecture, we'll briefly go over the mmap operation, and then next time when you run some different mappings and demand paging, copy and write, and more complicated concepts, and we will revisit mmap operation. But for now, let's take a look at this first part. So this is kind of part one, mmap. So mmap takes this parameter. PTR is the location where the mmap use it. So if you know, then operating system just kind of find an empty virtual address space and return to that. If we specified the operating system trying to allocate the address space that this PTR specified. Okay, so address and length is size, obviously, in bytes. Prot is protection, so it's executable bits. Read bit and write up bit, non-bit. No one can access. No read, no write. Why do you need to protect non? Why non is required? This is for further security. You may heard about the canary, where to detect buffer flow, buffer run, there's some kind of area that buffer run, detecting buffer run by setting the protect non, but let's not talk about that. We don't need to care about that. So this is kind of protection. Execute bit, read, write. And the flag is most important. It defines operation. So map private, map shared, map anonymous. Okay. The three important things I will discuss later of the meaning of private, shared, anonymous. FD and offset, file descriptor and file offset. So interestingly, mmap having a file descriptor. So if it's -1, no file descriptor. Why? So just kind of before explaining the operation, why mmap takes file descriptor? If giving the file descriptor to mmap, what does it mean? How can I implement it? To communicate with other process. This is also a good thing, but there is a different semantic. Why no? To communicate, yes, but here's another case. Do you remember that in the virtual address space, static area, dynamic area, static area, code and data, dynamic area, heap, and stack. When allocate this code, so this section each allocated by mmap, heap BRK, stack is just kind of using the stack pointer. There's no using the mmap BRK. This is mmap. Where does contents of code come from? Where does the contents comes from? Code section in binary, storage binary, right? So what does it mean? Open bin ls. Okay, so then it returns file descriptor and mmap file descriptor here. So that is meaning that the mmap operate where, if page fault happens here, then operating system take data from the where the file descriptor specified. So this is which is bin ls file, the operating system loaded. This is kind of file FD. Okay. So that means that some file contents are backed by storage. We can also locate some kind of this is a stack. This is a heap. And somewhere here by malloc mmap. Mmap some location, then returns pointer address returns as a result of mmap. Then file descriptor are specified -1 because this memory region is not comes from the file, which means the FD is set as -1. Then first application tried to access this region. Then what happened? What happened? Same thing, page fault happened. Then how operating system allocate this region? How does operating system allocate this region? This operation happened. So if map is allocate somewhere heap and mmap happens, and then the access happened, this page fault, 0 pages, and map in page tape. Operation happened. So this region is allocated at this point by zeroing that. So how to initialize this one? This one are different, right? So this one, there is a static area where content is stored in the disk. This area, content is not stored in the disk, and page allocated by zeroing. This type of memory called file vector. Okay, so this memory called anonymous memory, this memory called file vector memory. Therefore, when you allocate this type of memory, what map anonymous has to be specified. So map anonymous means that the file descriptor is -1, and I want to allocate some anonymous memory. That is kind of page is zeroed out and give it to application. What's that? And now private and shared. Let's take a look. So this is the example of the briefly what I talk about that. Memory mapping has this uniformity. Recall that the beauty of the Unix API, where a single mmap interface handle different type of memory. File, device memory, shared memory, none, which is called anonymous mapping. So basic concept of mmap is this one. As I said, mmap in here some area of heap, the mmap is backed by file. Also, it's possible. So you can open a file. FD and mmap giving FD, then this one working as a file vector memory. So memory map this size are exactly same as file length. So page fault happens here. The OS can finding this data and load operation happen. So again, access again, page fault happen. This contentful file. This is called file backed memory and giving file descriptor. FD. Device memory, shared memory, we will talk about later. Device memory will not, but shared memory we will talk about later. When we are talking about more page mappings and page mapping mechanisms. And the other one is none. I said that. So anonymous memory is not backed by file. So when page fault happen, operating system 0 and give it to application. That's anonymous memory. So all these four types of memory handle a single interface, which is called uniformity. All right. So this is a recap what I'm talking about. That file backed anonymous memory. So file mapping memory, file backed memory is regular file mapped in memory region to a file region. The contextual file can be written to load store instruction in the operating system. Anonymous mapping is virtual address space not backed by a file. So maps memory region to memory area is filled by 0. Okay, this is called zero-page mapping. I explained that. All right. So the other thing in mmap interface, private and shared. Private and shared. Private concept and shared concept is different. So in shared, multiple process can map a same backing store in their own virtual address space. So here's kind of illustration. So this is a storage. This is a file. And this is physical memory. This is virtual memory. This is a virtual memory. Process 1. Process 2. So in some case, this mapping goes to this physical memory. And this one also having a same mapping in process 2, which is called shared mapping. So therefore, in shared mapping, what is the semantic of shared mapping? When process wide, then the changes are applied to physical memory. So you cannot this modification immediately visible to other process. So modification to a shared pages are visible to all involved processes. That is concept of shared mapping, page semantic. Private mapping. So the private mapping modification is not visible to other process. Typical example of using private mapping is copy on write. For copy on write operation, we need to understand this diagram, and we will discuss later how mmap work after learning page table, how copy on write operation works later. We will discuss later. Talk about later. Okay, so that is the shared mapping semantic and private mapping semantic. So mmap can specify. Therefore, 4 angles are possible. There's a file-based mapping, or anonymous mapping, and there's private mapping and shared mapping. Private file mapping possible. Okay. Private anonymous mapping. This is by default. Default anonymous pages are private. Shared file mapping. This is also default in file mapping. Default file mapping cases. We're also having a shared anonymous map. This is called SHM, shared memory. Private file mapping is not popular, but private file mapping is used for some cases where in code section, but let's not talk about the meaning of the private file mapping. So that's private anonymous and shared file mapping, common, and shared anonymous mapping, which is called shared memory, SH. Data semantics of mapping. That's all for memory allocator. One more thing about this sharing. So let's extend this sharing a bit more for connecting with computer architecture. Sharing concept of virtual address space, virtual address 2. And this is physical address space, and this is file. And file are loading into this physical address space, and virtual address space are mapping this file and this file. So here, process 1, process 2, if process modify this page contents A prime, meaning that the physical address space also A to A prime, and did it apply this virtual address space A to A prime shared. So modification of P1 is visible to the other process. How? Do you know how this modification is immediately visible? What kind of, in computer architecture, what mechanism allows that this modification made by one process can directly visible to other process? What mechanism? Derived is, so we'll learn later. This is a bit like we can learn in the page table architecture. Then we talk about derived. Derived means page is modified. But I want to see two different systems are visible. Computer, if it took computer architecture, you not learn this concept. What is it? So this is not related to operating system, but I want to let you know kind of the underneath of this one. So this is kind of connection point between operating system and computer architecture. What mechanism allows this kind of sharing? Snoop, okay, you're getting there. Snoop, so what? GPU cache. So let's say this is a process 1, core 1, core 2. So they are usually having a shared cache. So process 1 is changing data, cache line. So this modification is just kind of CPU cache modification that is back to DRAM. So before this cache is written back, evicting to DRAM, the cache line of first modified A1, A to B. A is A to A prime. Then this cache is shared, so it can be visible to other process due to this cache, shared cache. Do you learn how to, if multiple shared cache, so say this is 2 core, and if we process 1 here and process 2. Do you know what is it? Then this line has be consistent. This is by cache coherence protocol. MESI, MOSI, MSI. So in the computer architecture, we learn several kind of the cache coherence protocol where this cache line is coherent between these two. So that if modification happens, cache coherence protocol apply this other cache line, and process 2 can be directly visible. So under the hood, this cache walking into place. So therefore, this shared mapping works. Okay, so that's all for kind of most necessary knowledges about memory API and shared mapping, and what kind of computer architecture comes into play to allow this directly visible shared mapping. All right, so that's all for today, I think. And then last time we will go on how the mapping mechanisms, or branch and bound segmentation and paging and etc. The other mapping mechanisms, and talking about pros and cons to continue the virtual address abstraction. Okay, so that's all for today, and I hope you have a good Chuseok holiday, and let's talk about the rest of stuff in next Wednesday. Okay, thank you, and talk to you next Wednesday. Bye. Good Chuseok, happy holiday, guys. Take care, guys.